Hello, welcome to this lesson of our study of how do I call it, Fourier series. Okay, so basically we have many applications of Fourier series, and in our subsequent videos we'll be even applying Fourier series in solving some PDs. Okay, but here we are just coming to look at how to find the Fourier series of some given functions. Okay, alright, so Fourier series. Given a function, okay, f of x, for x within this range or within this domain, okay, this interval, then a Fourier sine series is given by f naught. I name it naught as odd because the sine function is odd. Okay, it's odd in nature, so I'm just saying that the Fourier sine series is an odd function. Okay, it's given by this expression. The summation as n starts from 1 to infinity bn sine of n pi over l multiplying x. Okay, so this is what you have, where your bn is proven to be given by 1 over l integral minus l to l. That is the range for the integral. F of x, this f of x is what we are talking about. Okay, the f of x given in the function, multiplying sine of n pi over l multiplying x. Okay, I hope you copy these. So this is the formula for bn. That is the formula. I want you to just keep this. Okay, now I go to the Fourier cosine series. For the Fourier cosine series is given by, that is the fe. I call it fe because it's an even function. Okay, it's equal to a naught plus summation n start from 1 to infinity an cos of n pi over l x. Okay, so that is the summation used for the Fourier cosine series. And with this particular one, a naught is also given by 1 over 2l integral minus l to l f of x dx. So keep this a naught. Okay, keep this formula. And then an is also given by this 1 over l integral minus l to l f of s cos of n pi over l x dx. Okay, so you do this, you find all these values, then it means you are done. Okay, you just come and put your constants a naught, an, and maybe bn, depending on which type of Fourier series you are being asked to find. Okay, so if you are being asked to find Fourier sine series, you use this. Okay, with this integration. So this with this, you should know that integration is very, very crucial in Fourier series, so that you'll be able to integrate and get your final value. Okay, so know your integration very well. Okay, so the total Fourier series is given by f of x equals f naught of x, that is the odd side, that is the sine, plus the cosine part. Okay, my pen is not coming. I mean this part. So this is what we have. Okay, the sine plus the cosine. And now if you do the computation very well, this is what you have as your final answer, that you get your total Fourier series to be a naught plus summation n equals 1 to infinity an times cos of n pi over lx, then bn times this, where your an, a naught, and bn are given. Okay, so note for a function g of x. Okay, this is a very crucial point I want you to notice here. We'll be applying these, but not always that this will work. Okay, so note this. Some students or some people confuse the Fourier sines, that is the Fourier coefficients, these ones with putting some 2 in front and those stuffs, but they are all coming from this notes I've written here. Okay, so note that if you have a function g of x, okay, then if g of s is even, then when you're integrating g of s over a symmetric interval, that is, the symmetric means minus l to l, and then you can break this at 0, so you can do it as from l to 0. Okay, then union 0 to l. This will give you back this, so it's symmetric at 0, so you can just break it at that point. Okay, then with that, if g of x is even, if it is even, then we can say that our final integral, that is from integral of g of x from minus l to l dx, when g of x is even, then it will be equal to 2 times the integral from this time from 0 to l g of x dx. Okay, And now if g of s is odd, then the whole of this integral over a symmetric interval is 0. That's from minus L to L is 0. I hope you understand this. Now let's go to another one. Again, if you have two odd functions multiplying, so if you have an odd function multiplying an odd function, you get an even function. The final result will give you an even. If you have an even function multiplying an even function, obviously you get an even function. But if you have an odd function multiplying an even function, you get an odd function. So know this, because if you remember in the Fourier series, yes, we have f of x multiplying cos in the an, and we have f of x multiplying sine in the bn. But you know that cos is even. Okay, this is even. So if I have an even function here, if f of s here is even function multiplying the cos, obviously we get an even function at the end. Okay, so that this whole thing, we can use the idea we have here to change it to this. Okay, that time it will change to 2 over L, then the minus L will turn to 0. Okay, then use the same functions inside here. But if it is odd, okay, if everything here is odd, then we'll get 0. Same applies to this part. Okay, if it is even, then you apply whatever you know, the even function approach. If it is odd, then this whole thing will get you 0. Okay, I hope you understand. So keep the formulas, that the ones I've given you, so that let's start with an example. Find the Fourier sine and cosine series of f of x equals x for this interval minus L. Okay, let me use the yellow pen. Minus L to L, x within that interval, and then our f of x here is given as what? X. So to solve this, very simple, very, very simple. Okay, we just need to Fourier sine series. We just have to, the question is asking for the Fourier sine series and Fourier cosine series. So we just need to write a Fourier sine series formula down, which is this, and then Bn, which is given by this. But here our L is the highest limit of x, and that is also L. So that one, we just keep it that this is L, and our f of x here is given as x. Okay, so we just have to substitute what we have here into the B formula and solve for Bn. Okay, so therefore our Bn will then be equal to 1 over L integral minus L to L. F of x is what? X. Then sine of, we are looking at the Fourier sine series, so this is the Bn, n pi over L x, then dx. Now let's consider the x. F of x equals x. It's an odd function. Why? Because we said an odd function is a function that f of minus x will give you minus f of x. Okay, now let's look at f of x equals x. When x equals 1, you have f of 1 equals 1. When x equals minus 1, you have f of minus 1 is equal to minus 1. Okay, but this one here, this one that we have here without a minus, is actually f of 1. So f of minus 1 is actually equal to minus f of 1. And that implies is that f of minus x equals minus f of x. This time around our x was 1. Okay, so it makes the x an odd function, and then we already know that sine is also an odd function. So the product of two odd functions, what would that give? Okay, we said that odd multiplying odd, that's what I just showed before coming here. Multiplying odd will give you an even function. Okay, so this actually means that the function under the integral sign, at the end of the day, will have an even function. So Bn will be equal to, we said if everything here is even, then you can write this as 2 multiplying that integral. Okay, we said it, I don't know if you remember, let's go to the previous page for you to understand what I mean. I said if g of s is even, then the whole of this integral from minus L to L will change to 2 times the same integral, but then the limit will change to 0 to L. Okay, then the same function under it. And we also said that the product of two odd functions will give you an even function. So in effect, this is what I'm trying to apply, that the product of x and sine will give you, x is odd, sine is odd, so it give you even. So therefore the whole integral will give you 2 times whatever integral we have, and that is 1 over L integral from 0 to L, because we said it's even, you change to 0 to L, then the same function will come, sine of n pi over L x, then dx. And this whole thing will be equal to 2 over L integral 0 to L x sine of n pi over L x, then dx. So we realize that the only part we have to solve is this integral, okay? So let's pick that integral 0 to L x sine of n pi. I could have picked a simple example, okay, but let's do this together so that we remind ourselves of some integrations, okay? Now let's use this integration by part, where we set our u to be equal to x. Why? Because when you differentiate to u, it will give you a constant. That will be simpler for us to do. Then our dv to be equal to sine of n pi over L x. Then du is equal to 1, and v is the integral of sine, and that will be equal to 1 over the differential of the bracket inside, and that will give you n pi over L, and 1 over that will give you L over n pi. But when you differentiate, when you integrate sine, you get minus, so there's a minus in front of this, then cos of n pi over L, then x. This means that our integral x, that is 0 to L sine of n pi over L x dx, then because uv, this is what you do integral of v du or u dv. Yes, u dv is equal to uv minus integral of v du, right? So this is what you are going to use. Now we said our u is actually x and our v gave us this, so we have minus x times L over n pi cos of n pi over L x, then minus v du, and this is our v, and du gave us 1. So in front of the v we have minus already, but then there is a minus in the formula already, so negative will affect the negative, and then at the end we have plus integral 0 to I want to bring the limit. I want to finish everything before. Okay, so let me bring this minus this out. When I bring it out, it will affect this one, and that one will give us plus. So we have plus L over n pi integral 0 to L. Sorry, I said I won't bring the limit. Cos of n pi over L dx. Okay. Now, if you can see clearly from here, you're going to get some things. Okay. I actually don't want to write the answer straight. Let's do it together. So in effect, we have minus x L, or maybe Lx, anyhow you want to write it. Okay. Lx over n pi cos of n pi over L. Then how do I have here? I have plus L over n pi. Then when I integrate cos, I have sine, okay, but then I'll have to differentiate the bracket there, okay, because remember in the integral you have this there, cos of this, and then there is an x somewhere. I think here too there's an x here, okay. Kindly bear with me because it's plenty here. Then we'll have L over n pi again. When I differentiate inside the bracket, I'll have L over n pi over L, but then it's 1 over the differential, so I have this. Then the sine of n pi over L, okay, the whole of this. Then there's a final integration that you have, so you just bring your limits, okay, because if you bring the limits before, then you have problems. So I have this. Now let me put L inside this first. When I put L inside, I'll have L inside the x part here. Let me show you where the x's are. I have x here, I have x here, and I have the sine part. There's supposed to be an x, sorry. Okay, I have another x here as well. This is coming from the integral of this, integral of cos of n pi over lx. Okay, there's an x here, and I said that you integrate cos, you get sine, but when you differentiate whatever that is there, you differentiate n pi over lx, and this will give you n pi over l, right? But then the integration takes the reciprocal, so you have to divide by 1. Okay, so it will become 1 over the whole of this, and when you simplify that, you get l over n pi. That is what you have here. Okay, but then before, you have l over n pi in front before this, before the other one, that is before this one came. You already have this already. Okay, so you have to keep that. So when I put, like I said, when I put s equals l here, in terms of here, the first part, the first term, this part, I'll have minus l squared, okay, over n pi, and cos of, when I put x equals l here, it will cancel this l. Okay, there we have n cos of n pi over lx. So when I put x equals l will come here, and then this will take this out. So we'll get cos of n pi. Okay, cos of n pi. Then I come to this side and put x equals l here. But then let's multiply this and this first. Okay, we have plus l squared over, how do I call it? I have n squared pi squared. Okay, then sine of, when I put x equals l inside, I have n pi, the same thing. Then all of this here, okay, minus, okay, and I have to use the yellow one. When I put 0 in, there's an x here, so when I put 0 in, everything goes to 0. Although cos 0 is 1, but then because of this x here in front, it will go to 0. And then sine of 0 to happen here, and sine of 0 is 0, so actually we have 0. And that will be it. You close the bracket like that. But sine of every n pi, this n here is integer multiple. We have summation starting from n equals 1 to 2 to 3 to 4, the rest. Okay, and that n here, so sine of every n pi, you can change your calculator to radians mode and check sine of 1 pi, sine of 2 pi, 3 pi. You see that you are getting 0, so it means this part will give me 0. Okay, so we are left with minus l squared over n pi cos of n pi, and then cos of n pi is also either -1 or 1, depending on the value of n. Okay, so you check cos of 1 pi. Okay, cos of 1 pi is -1. Cos of 2 pi is 1. Cos of 3 pi is -1, meaning that cos of n pi is actually -1 to the power n, where n is 1, 2, 3, and the rest. Okay, so I have minus l squared over n pi, then -1 to the power n. Okay, you can go ahead and still do other simplifications to this, but remember, this is only the integration part. Okay, I mean, only this part gave us what we have right now. So bn is actually equal to 2 over l times that. Okay, so bn is actually equal to 2 over l times our integral answer, and the integral answer gave us this, minus l squared over something over n pi times that. Okay, so I have minus l squared over n pi okay, then -1 to the power n. You can keep it like this, or you can go ahead and simplify, where l here will take one of this l out, so we'll have 2. Okay, you have 2l over n pi. Remember, there's a minus in front, so I have -1, then -1 to the power n. Now I'm seeing some indices here. Okay, -1 and -1 are the same, so I have 2l over n pi, then minus 1 to the power n plus 1, because the power here is 1 here, and that when I do this, what I have. So actually this is my Bn. Okay, so therefore my Fourier sine series, okay, my Fourier sine series, which is the f naught of x, I call it that way, summation n equals 1 to infinity, then Bn sine of n pi over Lx is now equal to summation n equals 1 to infinity. Our Bn gave us what? 2L over n pi into negative 1 to the power n plus 1, then sine of n pi over Lx. And this is our solution. Okay, this is a solution. You can go ahead and maybe try to simplify this, or maybe pull the 2L over pi out, because they don't have any n inside, so they can be pulled out and you'll be left with something like 2L over pi, okay, summation n equals 1 to infinity, then minus 1 to the power n plus 1 over n, then sine of n pi over Lx. Okay, you can also keep it like this. So anyway you keep it, that is the Fourier sine series, okay, for the question. Now let's go to the Fourier cosine series. Okay, remember we said that the limits for x is minus L less than or equal to x less than or equal to L. These are limits we have, or the domain we have. Okay, now a naught is equal to this, and when I put it inside, I have 1 over 2L integral minus L to L. F of x is equal to x. That was the question given. F of x was equal to x. That same question, you will find the Fourier cosine series. What we just did is for the Fourier sine series. This is what we have as a solution, or the down one. Okay, now you're looking at the Fourier cosine series. Now for the Fourier cosine series, like I said, this is your a, and then you have the x. But what is x? X here we said is an odd function, and we have a term that if you have an odd function and you are integrating over a symmetric range, then the whole integral will be equal to 0. So a naught, which is equal to 1 over 2L integral minus L to L, okay, x dx. X here is an odd function, so this will give you 0. Okay, it's a symmetric domain or symmetric range that you're integrating over. You can actually integrate this systematically and get 0. You can try that one and check it out. Okay, your an is also equal to 1 over L integral minus L to L x cosine of n pi over Lx dx, because it's f of x cosine of that, and f of x is x. Now we have x is an odd function. Okay, so we have a product of odd multiplying cos is an even function, even, and we said the final answer will give you odd when you have odd multiplying even. So at the end of the day, the whole of this is an odd function. The product of what we have there is an odd function, and we said when you're integrating an odd function, the whole of this will give you odd. So it's like we are integrating an odd function. That is what this means. Okay, and we said that when you're integrating an odd function over a symmetric domain, then you have to get a 0. The answer is 0. So an is also equal to 0, meaning that the Fourier cosine series here is actually equal to 0. You are done, because when you come and put an and a naught inside, okay, here give you 0, multiplying everything, here too is 0, so it means we actually have 0. Okay, now with this, the total Fourier series will be equal to f of x is equal to f naught of x plus fe of x. Now this will be equal to 2L over pi. That's what we have for the odd function, that is the sine side, infinity minus 1 to n plus 1 over n, then sine of n pi over Lx plus 0, because the Fourier cosine series is actually 0. So this is a Fourier series for the function f of x equals, so this is for f of x equals x, for x being in this region. Okay, this is what you have. That is the solution to that Now let me give you a trial one so that or let me say something small. Note this, that if f of x is a piecewise function, you can see that from here f of x is equal to a, where when x is within this range, and it's equal to, here is supposed to be less than or equal to, and it's equal to b when s is within this range. So if you want to write the Fourier sine series or the Fourier series, the coefficients are given by an or a naught is equal to 1 over 2l integral minus l to l, then f of x ds, right? So now what you have to do is you have to write your this is multiplying the whole of this integral, but in this integral is not that straight because f is defined at different points with different regions. Okay, so you just write 1 over 2l, and then the total integral will be equal to, starting from the first region, minus l to 0. What is your f of s there? Because this is f of s ds, so you put that f of s is a, then ds, plus you go to the integral from the last region or the last limit, 0 to what, l. Then what is your f of s there is b dx. This is how you do it. Okay, then you sum everything. After summing everything here, then you multiply by 1 over 2l. Same thing happens to an, and that one will be equal to, or will be given by this. Okay, so you'll be splitting them into two according to the regions for each piecewise function defined. Okay, and look at the function that is there at that point. So here in the first region, f of x will be a. So in that first region, you integrate with a multiplying cos, okay, for the an, and then the next region, that was from 0 to l, you multiply b to cosine of that, and that will be different. That will give you different values. Okay, so you simplify, and then the final answer multiply by 1 over l. Same thing happens to the bn side. Okay, all right, I hope you understand it. Now try this. Try to find the Fourier sine series and Fourier cosine series of the how do I call it, function f of s equals s squared within this region, minus l to l. Okay, now here realize that s squared is an even function, so I think when you multiply that s squared to sine of something, you get an odd, and integrating over symmetric region, you get 0. Okay, so bn will straight away be 0, meaning that the Fourier sine series will be 0. And go to a naught, and that one you can use the even function because s squared is an even, so you can apply that knowledge there, and this is what you are supposed to get. That's a naught, and for a n, this is what you get. Now after everything, your Fourier cosine series will be this one. Okay, it will be this one. That same thing will be for the whole total Fourier series because the sine series aspect is 0. I hope you understand this. So this is what you have for the Fourier series. Try this and let me know if you're able to solve these examples or this trial question in the comment section below. Thank you, and don't forget to subscribe to my channel if you have not subscribed. See you next time. Next time we'll look at half range Fourier series where the range is not minus l to l, but then you get something like 0 to l. Okay, something like this. What will be the coefficient? The coefficients will change, so stay tuned and just like my video and also share as well. Okay, see you next time.